All right, hi everybody. This is the third video for this project, the 60-second timer project. And the last time what we did was we covered how to do the input clock divider, the divide by 10, and then the pause control bit. Okay, so those were covered in the previous video. So if you are still looking at that, please take a look at those previous ones. What I wanted to cover today was how to do the count, the 0 to 59, and then the rollover. All right. And so when you are demonstrating, remember, here's kind of just a summary of what you need to do. You can work in a group of one or two. So either by yourself or with someone else. Everybody has to turn in a report. If you do work with someone and you're doing some communication online with that person, you can both have the same report, but I want everybody to turn it in. Okay, so that way I can see that everybody has pushed it up to the classroom. Okay, and then here's all the requirements for it. So make sure you have all of that when you put that report together. All right, so I'm going to bring up Multisim here, and I have it basically running in simulation mode. Then I've got the display showing, and what I want to do is just show you a demonstration of what I'd like you guys to show me, in that get a screen capture of this or just record it with your phone, and then that would be your quote demonstration that you can show me running out of simulation. Okay. So what I want to see is that you'll have a picture of you'll have screenshots of your circuit for one, but then when you have your demonstration of it working, I'd like you to zoom in on the displays. These displays here are common cathode, and I'm using the 74 LS48s. Like I said before in the previous videos, if you're using LEDs, that's fine. If you're using like Multisim Live and you can't get access to displays or the drivers, then you can just use LEDs, and that's perfectly fine. But if you're using Multisim Desktop, you have a version of it and you're using the license, then I'd like you to use the display drivers and then the displays. So you would use either common cathode with the 48s, right, 74 48s, or use the common anode with the 47s. Okay, so the 47s are active low inputs. That means that you would sync the current into them, and you'd have your common pin tied to VCC. But in this case here, this common pin, and I don't have it shown here, this common cathode here is down to ground, is tied to ground, and then these are providing high true outputs, meaning they're high when you want it to be lit up. Okay. And then that way the current would flow from here through the LED into ground, right? The other configuration using the common anode, the current would flow from VCC through the LED and then into the and sync into the 47, right? 7447. Okay, so those are just the two different options that you have in hooking up the displays. And we've talked about this already before. Just hook up these control bits, which are just like things like the decimal points and blinking and things like that. And we don't need to do that. So we just, because they're active low, that means that they would be a 0 to enable them, and we don't want to enable any of them. We want to disable them. So we tie those all to VCC. Okay, so these guys would all be tied to VCC. These four inputs here would be one of your digits. So in this case here, this one is going to the most significant digit. So these would be my outputs of my 163 counter. D, C, B, and A would be like QD, QC, QB, and QA. And then this guy down here is the least significant digit. Okay, so connect those up to your segments A through G. And then if I run this thing is set paused at 48. What I want to just show is that if I run it, I can see that it's changing 51, 52, 53. When it gets to 59, I should see it go to 0. Okay. And that's what happens. So you can rewind it. It kind of goes a little bit quick, but you can set it up for whatever it looks, whatever looks best for you. If you run the master clock too slow, it's going to just really grind, really be slow in this, the incrementing digit. So this one was good enough for me when it goes up to. It doesn't have to reflect, pure second tick marks, as long as you can get it, as long as I can see it. And we'll go through it one more time. So there's 51, 2, 3, 4, 5, 6, 7, 8, 9, and then 0, right? So I shouldn't see it go to 60, right? I shouldn't see a 60 flash up, even though it looks like it's a little bit kind of glitchy here. What I should be able to do is verify that from 59, it just goes directly to 0, okay? So you have to have that do a detection of the digits 5 and 9. All right, well, how do you do that? Okay, so this is what I'll cover today. Here are the two 163 counters. We've got a least significant digit here, a most significant digit here. We've already talked about how you connect them up in cascade. If I want to connect a low to a high digit, the way that I can do that is by routing to the ENP bit of the more significant digit. All right, and if we were having this thing count just up in binary, where I wanted this thing to count to the terminal count, and the terminal count for 4 bits would be 1111, right? So that would be a 15 here. And what we saw with the RCO from the last video was that the RCO will go to a logic 1 whenever these 4 bits are at the count 1111. Okay, so RCO is meant to tie into the ENP if you were to count this guy up to terminal count and then you wanted to bump this more significant digit by 1, right? You want to increment it by 1 each time. All right, but what we don't want this thing to count to 1111, right? We don't want it to count to F. We want this thing to count to a 9, right? Because we are having this thing increment in as a second counter. So it should go from 0 to 9, right? And then 10 to 19, then 20 to 29, and so on, right? So that means that this guy here has to actually generate that little pulse like an RCO pulse when we are at the 9 count for this thing, right? So we want this thing to count up when it turns into a 9. All right. This least significant digit, I've got both the ENT and the ENP tied to VCC. Right. So if I follow it all the way over, there it is, 5 volts, VCC. So this guy's always going to count, and that makes sense. I mean, it's counting continuously as the ones digit in the second counter. It just keeps counting, right? It never pauses. The more significant digit here is going to increment, and then it just holds, right, until this lower one counts from 0 to 9, and then it's going to increment again, and then it holds. Then this one will go from 0 to 9, then this one will increment and hold again. All right, so this guy here is tied to VCC because we want it to increment all the time. This one here, I'm tying the more significant digit. I'm going to tie the ENT to VCC, right? Just let that guy go, but I'm going to control it with ENP, right? That's the typical way that we control it. We just let ENT be tied up to VCC to enable it, and then P will be the one that actually controls it. All right, so in this digit, let's look at the least significant digit here. Okay, so I have a load here going off, and then I have another load going off in here as well, right? All right, so the question is, well, how do I control both of these? Okay, so let's look at the least significant one first. I have this load going all the way over to this set of logic here, and if I follow it, it's active low, right? So this last thing is the inverter, so that's just going to invert the bubble there, right? So the main part of this control is going to be all of this stuff in here. Okay, so all of these logic gates here are controlling when this thing is going to load. Okay, and then what are we going to load? Well, it's a synchronous load, so that means that when this load goes true, and true in this case will be a low, so it's always going to be high until we have that load being a 0, right? And so if I were to look at it with a probe here and then run my simulation, I would see this thing always be 1, and then it would drop down to a 0 when I'm going to load. And then when that drops down to 0 on the next clock, because it's synchronous, it's going to load in whatever these 4 bits are, whatever it has on them. And these things right now are set to 0, right? So it's if I were to follow that all the way through, it goes to ground. Okay, so they're set to 0. So 0, 0, 0, 0 are set to D through A. Similarly, I have the other one set to 0, but that's just because we're going to be resetting right at 59, right? We're going to make it go back to 0, 0 for both digits. So this one's going to 0 based on this load pin, which is going to be different than this load pin over here, right? So don't, it doesn't go into both of them. We want this thing to load back to 0 whenever it hits this logic here. Well, what does this logic do? Okay, well, if we look at it, we're going to see that we're tapping off of the output lines. We got to tap off of QA, QB here, QC here, and QD here, right? All right, well, those 4 bits represent one of the counts, right? Well, if I decode, the question is, well, what do I want to decode? Well, if I want this thing to roll over after 9, right? I want it to come from 0 to 9 and then roll back over to 0, then it would make sense to decode a 9, right? Because once we get that 9, then I'll get a signal here that says this is true, right? 9 is true. I'm at the 9 count. I'm going to invert it so that it hits the load, and then it'll go down to 0 whenever we hit a 9. And that way on the next clock, it's going to then load whatever comes in this D through A, which would be 0, right? So it's going to count from 0 to 9, and then it's going to detect the 9 here, and then load it back to 0, and then go count again from 0 to 9. Then when it hits 9, it's going to load the 0 back again. Okay, so that's how we're going to detect that. All right, so that's pretty straightforward. If you were to then just let this thing run, you can do this. You could do this first, right? Just to see that you've got your ones digit counting from 0 to 9, 0 to 9, 0 to 9. Just going to do that over and over again, and you would do it that way, right? Just set up your 163, detect wherever you want to roll it over at. In this case, we want it to roll over after 9, and then so we detect the 0. We're going to detect 9 is in binary as 1001, right? So here's the 1 here. That's the least significant bit because that's QA. Here's the 0 and 0. I know it's 0 and 0 because I have the inverters here, right? So if I get a 0 and 0 in here, I'm going to get a 1 and a 1 here. Then my AND gate will be a 1, and then this AND gate will be a 1 if this one's a 1, right? So when I have a 9, I want it to be 1, 0, 0, 1 across my QD through QA. So I'd have a 1 here, a 0 here, a 0 here, and a 1 here. It would AND all together to be 1 and 1 here. This would be a 1. Then on its output, then it's going to be inverted to feed into the load because that's a bubble there, right? Okay, so if I were to run that then, I should see then this thing, it's at 1 right now, it's loading, and if I were to back off of it, when it goes to 6, 7, 8, I'm going to see that go back to 0, right? So you could, if you maybe rewind this video, you'll be able to see it. Every time it goes to 9, you'll see it go to 0, and then it goes back to 1 whenever it's on anything other than 9, right? Okay, so that will load that least significant digit. Okay, so then the challenging one, or the one that's a little bit more tricky, is the most significant digit. All right, well, we want that thing to load whenever we have a 5 on this output, right? Because we want it to go from, we're going to count the most significant bit as a 60-second counter, so we want it to go from 0 to 5, and we want it to go back to 0, right? Well, we want it to go back to 0 when it has a 5 on the digit here, but also when we have it as a 9 on the least significant digit, right? Because if you just had it decoding a 5 all by itself, then as soon as it hit 5 here, for example, when it was 50 or 51 or 52 or 53, all of those would fire this part of the logic here, which is decoding the 5, right? And this is the 5 is just like we did with the 9, except this is going to be 5 here would be 1, 0, 1, and 0, right? So least significant bit would be a 1. The most significant bit is QD, so that would be 5 is 0, 1, 0, 1, right? So that would be a 0 on QD, 1 on QC, 0 on QB, and a 1 on QA to represent 5 binary. Right, so here's my QA. So here's the 0, right, because it's an inverter. And then my next bit would be a 1, and then my next bit is a 0, and then my next bit is a 1. All right, so this is decoding 5, but I also need it to decode not just 5, because if it hit 5 as soon as this thing rolled from, say, 49 to 50, then this would be true. And if I just used that strictly into my load, I would see it go to 50, and then it would go right back to 0, right? It wouldn't count up to 59 before it rolled over. So I have to add in addition to just the 5, I have to also add in the 9 from the previous stage, from the least significant digit. So then I have another AND gate here for this case here, which is the 5 for the most significant digit. This case here is the 9 from the least significant digit, goes into this AND gate, and when those two things are true, then I'm going to invert it, because I'm going to go up to the load of this digit right here. Okay, so 5, you have to make sure that you decode not just 5, 5, you got to decode 5 and 9, and that's what this AND gate is doing. The 5 from here and the 9 from here, invert it, and then it goes back into here. Okay. All right, and then we want this thing to count, we want this thing to enable and to increment when we have this thing going to 9 as well, right? So just like when we load the 0 into the least significant digit, we're rolling it over, we also want to then, when we do that rollover from 9 to 0, we want to bump the more significant digit by 1 as well, right? So not only is it going to load the 0 or reset, our least significant digit from a 9 to a 0 here, it's also going to bump up the next one, or allow it to count by setting the enable bit to a 1. That would allow that to happen. Okay, so if I, again, put a probe here to see when this thing is going to be allowed to count, and I run it, I'm going to see it basically reflect the same thing as this load, except just the opposite state, right? Because it's not inverted. So this is an active high input. So as soon as this thing goes to a 0, this will go to a 1. And we should see that happen there, right? So you saw it. And now if I show the digits as well, you can see 4, 5, 6, 7, 8, and 9. I'm going to see a 1. That thing will bump this one, and that digit will increment. Okay. All right, so I think that is pretty much it. That's all you need to really do for this 60-second counter. So take a look at that, implement that, show me that you've got it working. What you would have done if we would have been in class is that you would have actually built this with 163s. We would have created a clock that was like 10 hertz, and then you would have done a divide by 10 on it, and then I could have timed a minute with your 60-second timer. Okay. All right, so that covers the remainder of this project. So I'll give you the rest of the time to work on it. I think I have this thing, hopefully giving you plenty of time to do this. This is due on May 25th. So you've got a full, almost a week, more than a week to work on this. Okay, so that should be hopefully enough. If you have questions, shoot me an email, and I will clarify things, or if we need to do a live session, we can do that as well. Okay, thanks everyone.